H5L3 process, it is the third generation of H5L reactors. Instead of using 4 fixed bed reactor, which is used in the first HPI, a single moving bed reactor is used along with reforming plant, auxiliary equipment and quenching towers. So, reforming plant is essential part of most of the gas based process. So, 70% pellets and 30% lump are a lump ore along with 5% non-sticking ore are fed into the reactor. Non-sticking ore ensures uniform burden distribution. So, sticking does not occur. Operated at high top pressure up to 5 bar, automated system of valve enable the charging. So, this is a typical flow sheet of HYL3 process. So, as I said, reformer is the essential part of this gas based natural gas based process. So, natural gas comes fuel for heating it up. This is a reformer by which to get the proper CO and hydrogen content into the gas, and this is fed again into the sort of gas heater at the desired temperature to increase more when you condense the remove the H2O, and this this is just burner and not heater, not a reformer, and those heated gas goes to the reactor. So, this is the fluidized section actually. So, that is where these gases goes from the bottom of this and go up, and the iron ore is coming down in this one. So, that is where the most of the reaction which is occurring, and the top gases now again goes back and you utilize them either heating and heating of the these reformed gases, and then some natural gas to put it there, because this is a fluidized bed actually. So, mostly it is in fluidized condition. So, iron ore actually diameter is less, size is less in that. So, it gets reduced in the fluidized condition and quite hot. So, you need a sort of a cool or natural gas, not that heated, which cooled it down, and it comes into form of DRI from the bottom. So, this is the sort of essential operations of not just H5L3 process, many of the fluidized bed process, these are the essential part of it. Sometime in some of them, if it is hot, they put the briquette machine to make it into briquette form of this hot iron, directly reduced iron. So, it comes into the briquette form. So, descent rate is controlled by rotary valve at the exit of the reactors. So, here you have a rotary valve by which you control this exit descent rate. Hot reducing gases are fed from the top, and the cooling gases are injected from the bottom part of the reactors as said before. So, cool DRI is discharged through a sealing mechanism. Combustion chamber is installed at the reducing gas inlet to maintain highest possible temperature. Partial combustion improves the carburizing efficiency of the gas, and independent reforming and reduction reaction help the stabilization of the operation in the reformer. So, these are the features of H5L process of fluidized bed 1. Remember, Midrex process is not a fluidized bed process, it is just a peg bed process. So, that is a basic difference, and most of the production, I think almost 67% or so, as we saw in that figure, comes through this of the world, and remaining comes from this, and SLR are in process. So, typical problems faced in DR plants usually in the gas based you have a fluctuation in composition of natural gas. So, it sometimes become difficult to maintain the right composition, always some fluctuation is there. So, one has to be quite careful in that one and keep on checking the composition. Failure of the reformer tubes, this is also quite common problem in the gas based reformer units. Sticking of materials, this is one of the major problem, especially withdrawing the material after reduction and some low melting gang or something has formed, so some sticking problem may occur, and that's quite prevalent. Channeling inside the blast and inside the shaft furnace similar to the blast furnace. Product is pyrophoric and needs briquetting. So, especially if it is a fluidized one, because the size is small. So, it is like a pyrophoric in that one, so you need a briquetting before it comes out or exposed to the atmosphere. Contamination of expensive catalysts, especially with high sulfur needs. So, these are few problems with the gas based, and in the coal based fluctuation in the raw material chemistry. So, though still it accepts a wide variety of composition, but still one has to be careful in the chemistry composition of the raw material. Ring formation, that is related to more about the kiln based DR processes. Product invariably contains around 1 to 2% charge. Poor reactor availability, particularly in large plant. Process control is relatively difficult. Product cannot be hot charged or hot briquetted. That is also one problem in the coal based plant than the gas based plant. So, these are the few problem in both of them, and this is also one of the reason, not only just this, the main reason is about, as I said, it gives a sort of solid product, and so does not retain the sensible heat, and in the hot when you get it the liquid form, like from the blast furnace the liquid metal, it retains the sensible heat and which can be used in the steel making operation at the later stage. However, in this one, because again it has to go to the electric arc furnace and others. So, one again it has to be heated up to the melting point to make the steel, and this is one of the reasons till now these processes, though they use coal or gas, but they are far away to take over the blast furnace. In last half a century or more than that, hardly even a less than 5% is the contribution to the total hot metal production in that case. But nevertheless, due to many other advantages, a smaller unit at a smaller places, using of coal, these are still quite popular at a small scale. Now, we will do an example, and this is more based on like a soft type sponge iron unit. So, determine the pressure drop in this shaft of a sponge ion production unit from the following data. I try to modify I've modified this assuming the reduction gases or reducing gases are coming from the combustion of coal by air. So when you are saying the reducing gases is coming by combustion of coal by air, so you would be having a CO, CO2 and nitrogen into this. So like a blast furnace sort of gases. So under that condition you have to determine the pressure drop in the shaft. So blast rate or the gas rate is given 1400 normal meter cube per ton of hot metal. Production rate is 2800 tons per day. Average shaft diameter is 10 meter. Average size of solid 4 centimeter. Average temperature 700 degrees Celsius. Average pressure 1.5 atmosphere. Void fraction is 0.35. Length of the bed may be taken as 15 meter. Viscosity of the gas may be assumed as 4 into 10 to the power minus 4 grams centimeter second. So given these data, we have to determine the pressure drop. So naturally we need to know the Reynolds number, and not only Reynolds number, we need to know the density of the gas. So we have to density of the gas we can find out only once we know the composition of the gas. So those are the few essential things which we have to find out first, and then only we can go for the pressure drop. And for pressure drop we can use simply the Argon equation as we had discussed in the case of blast furnace. So let us see the 1 atmosphere initial we can consider, and 273. Now 700 degrees Celsius the process is operating. So it is 973 Kelvin. The rate is given the blast rate, it is 1400 normal meter cube per ton of hot metal. Actually it is per ton of wherever this hot metal is essentially direct reduced iron. So per ton of DRI it is. So it is a per ton of DRI. So total blast per day would be, we know already the blast rate and we know the production. So that will give us the total blast per day. So the total blast per day would be so much normal meter cube per day. Now in terms of second, we have to convert day into second. So 24 hours into 3600 second will give you the blast rates about 45.37 normal meter cube per second. So this is the blast rate. Now once we know the blast rate, we can calculate the velocity, because the shaft diameter is given. So we can use this relation. So we can divide by the area. So blast rate per second is nothing, area, cross sectional area of the shaft, and the gas velocity. So this is, we have already calculated 45.37 normal meter per cube, area is 5/4 into 10 to the power 2, diameter is given. So and then the velocity. And so, because it is a pi r square, that is why 4 is coming over here if we convert into diameter, and we notice the velocity. So, that really gives you the superficial velocity, and that is what we needed even for the pressure drop. So, this simply, if you rearrange this parameter, it will give you 0.577 meter per second the superficial gas velocity. Now, we know the gas velocity, we can also we can calculate the Reynolds number, but before that we need also the density of the gas. So, at 700 degrees Celsius, the equivalent gas composition would be nitrogen, CO and CO2, neglecting other small amount. So, we know it says 1.5 atmosphere it works. So, total pressure, the partial pressure of nitrogen, carbon monoxide and carbon dioxide should be equal to 1.5, and you know this cases which we are getting by combustion in presence of air. So, air you have partial pressure of nitrogen about 0.79. So, this we know if we substitute in this one. So, we get the partial pressure of CO and partial pressure of CO2 about 0.71. Now, so we know, let us say the PCO one of them having a partial pressure alpha. So, other one would be having obviously PCO2 equal to 0.71 minus alpha, because total is 0.71 of CO and CO2. So, now we have to use the reaction. So, CO2 plus C gives to 2 CO, this is quite standard one, and the free energy of the reaction is given by this. So, we can calculate the free energy from this. So, at we know the temperature 700 degrees Celsius. So, free energy for this reaction at 700 degrees Celsius is 3720.8 calories. So, now we know this. So, we can and we know the from this reaction the equilibrium constant of this reaction is nothing CO square divided by PCO2, and AC activity of carbon can be taken as 1. So, essentially it is a ratio of PCO square by PCO2. This we have done this sort of example before. So, I would encourage you to go look at the previous examples like this. So, PCO we have already assumed alpha. So, that is alpha square, and PCO2 we have calculated here is this. So, what now we need the K, the equilibrium constant value in order to get the alpha, and equilibrium constant value can be calculated using now free energy for this reaction. As you know, for that free energy with the equilibrium constant can be represented by this equation, delta G naught equal to minus RT log K. So, delta G naught we just now calculated, R and T in the proper unit is taken, then log then K. So, these are known, and K is the only thing which is unknown. One can calculate the K. So, K value comes to 0.1459. Now, this K value we can put it into this relation over here. So, we can get the value of alpha. It can be solved, all are known except alpha. So, this alpha gives 0.403. So, which is nothing, it is a partial pressure of CO. Then once we know this, then partial pressure of CO2 nothing, 0.71 minus alpha equal to 0.307. So, we got the partial pressure of CO and CO2. So, now we can we know the equilibrium composition of the gases at 700 degrees Celsius and 1.5 atmosphere, it is about in percentage 26.9% CO, 20.4% CO2 and nitrogen is 52.7%. So, from this fraction you can calculate this percentage. This has been done before quite a lot, and now we know this percentage or fraction of this thing percentage form, then we can calculate the density of the gas. So, we know at NTP, normal temperature and pressure, 1 mole of gas occupies about 22.4 liter, which is into 1000 so many cc's. So, the density of this would be 0.269 into 28, that is CO molecular weight, then 0.204 multiplied with the molecular weight of CO2 44, then 0.527 multiplied with the molecular weight of nitrogen and divided by 22.4 into 1000, that is going to give you the density of the gas, and density of the gas comes to 1.4 into 10 to the power minus 3 gram per cc. Now, we know all these and we know the Reynolds number definition of this one. So, we already got now density, we got velocity, diameter is given, viscosity is also given, void fraction is also given. So, we can calculate the Reynolds number. So, this is your density, velocity, diameter, viscosity, void fraction. So, viscosity is given, density we just calculated, velocity we calculated, and size of the particle is given 4 centimeter. So, that gives you the Reynolds number of 1242, and what this is applicable where we said Reynolds number is between this range, it is coming between only that range. Now, we can calculate the pressure drop, that is what actually is required or the question is asking, and pressure drop you know is given by the Argon equation which we had discussed before and those blast furnace example in detail, and Argon equation is given by this formula where phi is S is the shape factor and mu g is the viscosity and the gas velocity, gas viscosity, void fraction, gas density, particle size and the shape factor. Now, shape factor in this case would be 1 because the particles are spherical, that has been assumed. So, shape factor would be 1. So, now we can put these values void fraction, viscosity, this velocity of the gas. Now, SI unit here has been used. So, you can see the little difference in this, and then the particle size, void fraction, this is for this part and for this part is similarly can be given in this form. So, delta P over delta L is given so once you solve this is 21.33309, it comes to 330.47 normal per meter cube. Now, per meter now remember this we discussed about these two terms and we said this is more pressure drop due to laminar flow and pressure drop due to turbulent flow. So, you can see here turbulent flow is quite dominating, then the laminar flow is almost not just 10 times, almost 14 times or so than the laminar flow. So, total pressure drop comes into this, and which for the in the whole now this is on it. Now delta L is there, and delta L is given 15 meter. So if we multiply it with that, so our this comes to so many Newton per meter square, the pressure drop, and that Newton per meter square can be converted into bar. So it's about 0.05 bar. So hence the pressure drop in the actually shaft furnace is 0.05 bar. So that's the pressure drop. Now we will talk. Now we will switch over to the another process. So when we said alternative route of iron making, we said direct reduction, direct reduced iron, then we talked also smelting reduction. So these are the two main processes by which iron is produced in an alternative way. So direct reduced iron or direct reduced processes you are familiar now. The second process is known as the smelting reduction. So that is the one which we would be talking now, and as you are aware, in the direct reduction we said repeatedly that it gives the solid product. So sensible heat is lost, and what is preferred for steel making is in liquid form, and that's how the smelting reduction came into picture or into existence, using almost the same cheap raw material like coal, more fines, and like that. So now we will talk about the smelting reduction. So it is a new technology to produce liquid iron. In smelting reduction, liquid iron is produced directly from coal and ore fines concentrates. So liquid iron is produced directly from coal and ore fines. Liquid iron is preferred over solid iron, as molten iron retains its sensible heat and there is no gangue material. Another advantage is there is no gangue material. So slag formation is quite low in the subsequent process, where in the steel making using a DRI, it's more slag formation, and that creates another problem in subsequent operations. So now again, before we go to describing about the process smelting reduction processes which have been developed or commercialized, it's worth it to talk a little bit about the physicochemical nature of it, or the kinetics and reduction mechanism of it, as we had discussed for direct reduction processes. So in smelting reduction, most of the reaction occurs in the molten state with the involvement of liquid slag, which contains significant amount of iron oxide. Some important differences from the blast furnaces are: significant stirring exists in the reduction chamber. Post combustion influences the temperature. We will come to this term. I will explain a little bit, as you haven't come across this term, so I will explain a little bit later when we come to the process, that what does it mean, the post combustion. I will tell later. So iron exists in different oxidation states during smelting reduction, influencing the slag conditions, because it's continuously changing the oxidation state. Slag forming also influences the reaction. This also, I think, may be a new term for you. I will talk about it a little bit when I will describe about the process. So, kinetic aspect of this, because as mentioned, most of the reduction is occurring in the liquid stage. So, most of the reaction occurs in the molten state. So, reduction by solid carbon. So, if you sort of in liquid state, carbon solid produce iron and CO gas. In indirect way, even through CO gas it can be reduced. If you liquid state, gaseous state give iron and CO2, and CO2 again react with carbon, which is available to form CO, which again can reduce this. So, it is a sort of a diffusion rate controlling, but kinetics is quite complex as such in this one. Lots, okay, pure molten FeO and slag containing 80% FeO is called a zero order reaction. So, if the slag is containing 80% FeO, that is a mixture, then usually the kinetics is a zero order reaction. And if it is between 20 and 80% of FeO, then it is a first order reaction, and less than 20%, then it is a second order reaction. And usually this iron oxide rich slag with carbon kinetics is present by this equation, where n is a constant and t is the time and alpha is the fraction reduced, and k is a constant, and experimentally one has to determine. So, it is a quite complex reaction in liquid state, and not a sort of a very definite kinetic which is established, because it depends on many parameters. So, reduction by carbon dissolved in liquid iron, this of course we have seen in related to blast furnace in the hearth region. So, diffusion of carbon is rate controlling and partly controlled by fusion and decomposition of FeO. So, FeO also can decompose because it is operating at a very high temperature in the liquid state to Fe and O, and this solid carbon react with oxygen and form CO gas. So, this is sort of a diffusion rate controlling when reduction by solid carbon in liquid iron state, and reduction by CO, then rate of reduction is proportional to the flow rate of CO, the rate by which CO is generating. So, rate controlling step in this one is the mass transport of the gaseous phase, that is CO. So, related to kinetics of smelting reduction, it is about that much, which is a little complex, and quite a lot work has been done, but still there are many relations available in different conditions. But these are the main reaction which occurs, and rate controlling sort of a step or reaction, first order, second order, third order. These are the basic things one should be knowing about smelting reduction. So, advantages of this smelting reduction processes are use of fine ore. This is very important actually. Even in the blast furnace, mining and other subsequent operation in the raw material refining, lots of fines are generated in transportation. So, then you have to establish the agglomeration like sintering and pelletization plant and like that, and another energy intensive unit. So, and when in this process you can directly use the fine ores, and you are eliminating all those unnecessary units of agglomeration, pelletization, sintering, and a big saving in energy and environmental term in that way. Use of less expensive fuel. So, here you do not have to use even coke, and again one more environmental problem, and you can use coal directly and it is less expensive. No physical and chemical limitation, more productivity, low investment. These are also work like a DRI sort of way. You can put the small units at localized place. So, quite a low investment, in that way becoming a little popular. It is not no environmental problem, reduced environmental problem. Complete stirred system with immediate response to the change, like unlike blast furnace, when you want to see the effect of anything or any change, it takes hours. Here you will get the immediate response of any change which you want to do it. So, these are the quite few advantage of smelting reduction processes. So, smelting reduction processes can be characterized either a single stage smelting reduction or two stage smelting reduction. And the single stage smelting, okay, so shaft furnace process, Corec, Sumitomo, Kawasaki, electric arc. So, these are smelting reduction processes.